Relative dating requires no technology. It's based on common sense and reasoning and observation. Absolute dating, on the other hand, uses technology. It's more recently invented because it uses the concept of radioactivity, which was discovered by Marie Curie at the beginning of the last century. What's neat about absolute dating is that it gives us an actual number. For example, if I say something is Cretaceous in age or Jurassic in age, those are relative terms. They aren't numerical. An absolute term would be 90 million years. If you've ever wondered how scientists figure out how old stuff is, this is the day we talk about that. Radioactivity has a lot of complicated names. Sometimes it's called isotope geochemistry, which makes you sound really smart if you say it. Radiometric dating sounds pretty fancy. These just mean the same thing. Don't be impressed by the fancy terms. We throw them out in geology, and we don't always need to use such big words. Let's go back and review a little chemistry. If you're like me, you forgot a lot of your high school chemistry and could do with a refresher. This is a cartoon model of an atom. Why do I say cartoon? Well, because some version of this has been drawn and published in textbooks as long as they've been writing chapters on atoms. We don't actually know that it looks like this. Now, the middle is the nucleus. It's made out of protons and neutrons, which I can weigh. And then these tiny, tiny, very fast, energetic electrons circle the whole nucleus. Now, this is a virtual classroom. If it were a physical classroom, you might look around the room and see one of these. Most science classrooms have one. Maybe it's been a while since you thought about the periodic table of the elements. We're going to go through a refresher today, just how to read one of these little panels. Let's start with carbon. Sorry about that. I was getting excited with my Zoom function. Let's start with hydrogen, number 1, even easier. Okay, there's a little number. That's the atomic number. It's kind of like your student ID at El Camino. It never changes. Or your social security number never changes. Your atomic number, if you're an element and it's 1, you're hydrogen. Nobody else gets to have the atomic number 1. The symbol is just the letter we know you by, H for hydrogen. The mass is how much one atom of hydrogen weighs on average. This can change. This doesn't change. This can change. And remember that the mass is when I weigh the protons and the neutrons, and this number varies and varies and varies. What the heck is radioactivity? Well, it has to do with stuff that is happening in the nucleus of atoms. There are some atoms that we call unstable because over time they shoot off little particles. This one's called a beta particle, and you will not need to know different kinds of particles to do well in this class. But I do want you to know that we can have a change in tenance. Different protons and neutrons move out, and then we get new ones until we are in a stable daughter. Why they call it parent and daughter? I don't know, just tradition. Now, how long does it take for a nucleus to decay? How long does it take for an unstable parent to become a daughter? We call this the half-life. Here's a radioactive decay curve. Now, what this represents is if I have a brand new sample of a parent isotope. For example, I take something that's living. I take a leaf off of a plant. Well, there's a bunch of carbon in there. It's a living thing, and every living thing on Earth is made out of carbon. And while it's fresh, All of the carbon is made out of parent isotopes. Now they start to decay. After one half-life, half of the parents turned into daughters. After two half-lives, half of the remaining parents turned into daughters. After three half-lives, half of the remaining parents turned into daughters, and so on. Every single element will create the same shape curve right here. And by the way, this figure might be useful when you're doing the lab. Now, the geologic timescale already presented was made using relative dating techniques. It turns out you can't date everything. I know on TV and in movies it sounds like science has unlimited power to tell you how old something is. But of course that's not true. Only certain things lend themselves to radioactive dating. Now, if I look at this beautiful example of very famous rocks in the United States, only the ones made out of crystals, for example, this igneous dike, can be used with radiometric dating. The sedimentary rock is not good for that. And a lot of this earth is made out of layers of sedimentary rock. When we give a date in this class, it usually refers to a clue that was datable, that was somewhere in the vicinity to help us bracket the age and get an average of how old that stuff actually is. However, using the relative dating techniques, we can sequence things and then know if something is older than that or younger than that, relative age. The most famous example of radioactive dating, of absolute dating, has to be carbon. This is the one you hear about most in nature specials. Carbon-14 is a very famous unstable isotope. In fact, the daughter is actually called carbon-12. So carbon-14, very common in plants, I mentioned picking a leaf earlier, is useful for any organic substance. So it could be a rope, it could be a piece of cloth. This is a famous piece of cloth from Italy called the Shroud of Turin. And we can basically use this in archaeology sites. Humans make stuff out of organic material. Life forms are organic. They all have carbon-14. However, carbon-14 is only good for recent events. The half-life is short. This means all the carbon-14 decays and becomes a daughter every 5,730 years. Another half of the parent atoms have decayed. So this is perfect for stuff that happened in human history. Human history is pretty recent, geologically speaking. You would never use carbon-14 dating for stuff from the dinosaurs because all of the carbon present in your sample would have decayed a long time ago. It's too late to use that one. However, we do have other elements we use. I just wanted to mention carbon-14 because you might have heard about it in a National Geographic special.